Okay, we started talking about embedding of networks last time, so I'm just going to refresh your memory on that, and then we'll just pick up from where we left off last time. We have an undirected connected network with node set VCap, edge set ECap, consisting of undirected edges, and then we assumed VCap had n nodes in it, and the edges are undirected, and they are of the form VI Vj cap, where the pair ij comes from some set I. And we also assume length information is given. Lij is a positive length assigned to edge Vi Vj. Given this information, we talked about the embedding of this. Let me just change my pencil board marker. In the embedding, we need a space S in which we embed the network. The whole point of embedding is to speak of interior points of edges, because we want that to be a meaningful concept. So you need a space S for embedding. And typically, this could be the plane. In this space, we pick n distinct points, V1 up to Vn, each of which is a point of the set S. And Vi represents the vertex or the node Vi cap. Okay? And then we assume there's a mapping Tij which maps the unit interval 0, 1 into the space S. This is supposed to be a one-to-one continuous mapping, because we want it to be invertible. That's why you require it to be one-to-one, with the additional requirement that Tij evaluated at 0 is the point Vi, and Tij evaluated at 1 is Vj. Okay, I think this is how far we came last time, and I'm going to pick up from this point on. And I just had also a picture such as this one, V1, V2, V3, V4, V5, being 5 distinct points, and this is your space S. And so you've turned your network consisting of nodes and pairs of edges into a point set where your vertices now actually correspond to the old vertices, the non-embedded version. And your arcs are a little bit different. They are not pairs of vertices anymore, but rather they constitute a continuum of points between certain endpoints, which are vertices. Okay? And this is done for every ij, the set I. We take the point set aij to be the image of the unit interval under the mapping Tij. So aij is a subset of S, because every point that gets mapped is a point of the set S. All right. This can be done in such a way that the aij's do not intersect at any point other than the end vertices or the endpoints. So the endpoints of the arc aij, I'm going to refer to aij's as either arcs or as edges. The endpoints of aij are vi and vj. They are the end vertices. The embedding can be done in such a way that the arcs aij's intersect in at most one endpoint. So any pair of arcs either do not intersect, or if they do intersect, that intersection will be at a unique point, which is one of the vertices. Let me define additional concepts that we need for future work. Let's define vi, vj. Let me just use this notation to stand for the arc aij. So a bracket vi, vj is just another name for the arc aij. I'm going to define vi, vj to be the same point set, except endpoint vi is removed. Okay? This is similar to half open interval, closed interval, etc. So this is similar. It's the same thing with vj removed. And finally, vi, vj with parentheses rather than brackets. It's simply the entire thing with vi, vj removed. Okay. Length of the entire arc vi, vj is simply the number lij, which is given initially. And I need also some subarcs, which I'm going to define right now. I need subarc vix and subarc x vj. The intuitive meaning for these is when you take an arc with endpoints Vi and Vj, if you pick a particular point x on the arc, then that particular point defines two subarcs. One having endpoints Vi and x itself, the other one having endpoints x and Vj. That's the intuitive meaning of that. But to be able to make that somewhat more formal, I'm going to need the following definition. So to define these subarcs, let us first note that because Tij is a one-to-one mapping, its inverse exists. So let's name the inverse the function lambda ij. So let lambda ij be the inverse of the one-to-one mapping Tij. Which means that lambda maps the arc with endpoints Vi, Vj into the unit interval. It's the inverse mapping. So the domain and the range are interchanged with lambda ij of x, where x is a point in Vi, Vj. I'm taking a point from the domain of definition of lambda ij. So x comes from here. I assign to it some number, say delta. Delta is a real number between 0 and 1. So delta is a number in the range. And this is true if and only if Tij assigns to delta the point x. Okay? This is the inverse relationship between the two functions. Lambda ij of x is delta if and only if Tij of the number delta is the point x. That's the idea here. So, with that observation, we may now define Vix as follows. So let's just write accordingly for x in the edge Vi, Vj. The sub-edge Vix is defined to be the set of points y such that Tij of alpha, where alpha is a number, is less than or equal to the number whose image is x. So Tij of alpha is less than or equal to lambda ij of x for some sorry, no, this is not correct. Just a second. Let's correct this. Tij of alpha will be the point y for some alpha, which is in the interval 0 to lambda of x. Does that make sense to everybody? Yes. So you pick any point y as long as y is the image of Tij for some choice of real number between 0 and lambda x. Similarly, xvj is defined to be the set of points y in the arc such that Tij of alpha is equal to y for some alpha. This time, what interval do I want? Lambda of x to 1. Yes, that's the interval I want. You got the picture. If y is a point along the subarc from vi to x, then I may also define the subarc yx. So one endpoint is y, the other endpoint is x. What is the definition of this? It's the set of points u such that Tij of alpha is equal to u for some choice of alpha in the intervals where to where? Lambda of y to lambda of x. This all sounds very abstract, but if you draw a picture, everything becomes very easy. That's why it always helps to draw a picture. It always helps to imagine what's going on in pictorial terms, okay? However, when you want to prove things or when you want to devise algorithms, you need to use algebra. That's why you need all that stuff. However, insight comes from pictures. Yes? Yes. If you take the domain to be S rather than the arc itself, it would be into, but in this case, yes, it will be onto. Even though the arc does not have to be a straight line segment, let's just stretch it out so it looks like a straight line segment. Okay, so if I pick a point x, then my subarc vi to x is this portion. From here to here. X to Vj is this portion. And the length of this is how much? It's lambda of x, whatever that number might be. That's the length. Sorry, not the length, but the number between 0 and 1, okay? And this portion is how much? Whatever is left off.
So actually lambda of x times Fij.
No, I'm taking this right now to be the entire length to be 1. Okay, let's just put it that way, and I'm going to convert it to lengths, okay? So, since we're mapping the unit interval from 0 to 1, the entire length of this arc is 1 right now, okay? With no reference to the Lij's. Forget the Lij's for a moment. When Tij of 0, you get Vi, and Tij of 1, you get Vj. For anything between 0 and 1, you get another point in the middle, in the interior. Okay, so this is the situation where all of these numbers are between 0 and 1. And if I happen to pick a point y here, then I'm going to have lambda of y here and 1 minus lambda of y for this portion. And the portion between, how much is that? Yeah, lambda x minus lambda y. I don't know if you can see that. I had to make it kind of small, but that's what it is. Okay. So let's talk about the lengths now of these subarcs. Length of the entire arc, Vij, is Lij. That's just a positive number. The length of Vix is then going to be lambda of x times Lij. We're assuming the length is distributed homogeneously along the entire arc. That's what we are essentially assuming. So whatever the weight or the number that defines x is, that number also defines the length of the subarc. Okay? And the length of xvj is how much? The remainder is going to be Lij, the total length, minus this length. So whatever the length here is, from the entire length, you subtract that one, so you get this one. So this is the same as, of course, 1 minus lambda x times Lij. Okay, so again, if I continue with my picture, the length of Vi to x will be lambda of x times Lij. The remainder will be 1 minus lambda of x times Lij. And if you have another point y here, that will of course be lambda of y times Lij. And this will be 1 minus lambda of y times Lij. And finally, if you look at the segment between the two of them, this portion, the length of that will be how much? Yes, lambda x minus lambda y times Lij. Okay. So let's suppose you have an embedding N of the connected direct undirected network N cap, whose lengths are Lij's. So if I pick any 2 points x and y in the point set N, then I can define a length, a distance function for that. Define for any 2 points x, y in N, the function d by the following. D assigns a value to the pair xy, and it's the length, well, it's the length of a shortest path connecting x and y in N. Now, you are already familiar with the length of a shortest path from regular networks when you have node-to-node information. In other words, if you just have a non-embedded network, just this type of a network with lengths, if you pick any pair of nodes, you can always define a shortest path length between them. How? Well, if it's connected, then there's at least one path connecting those two nodes. And of all these paths, well, the length of such a path is simply the sum of the edges included in the path. And of all these such paths, you just pick one which minimizes the length. There may be more than one shortest path between a given pair. Nevertheless, the shortest length is unique. Okay? So that's well defined for regular networks that need not be embedded. For embedded networks, we had to extend the definition. That's why I had to go through all these painstaking definitions, because I had to have some sort of a definition for the length of subarcs. Otherwise, you cannot speak of that. So when you pick any 2 points x and y in the network, which may be end vertices, or else sometimes they may be interior points, then you simply look at possible paths connecting x to y. Since the network is connected, there will be at least one such path, and that path will consist of subarcs plus regular arcs, the union of possibly some subarcs and regular arcs. So whatever it consists of, you simply add up the lengths of those arcs. That defines the length of that path. And of all such paths, you pick one which minimizes the length, and that's the value of dxy. Now you had a question? Yes? N is an embedding. It's an embedding of the undirected connected network. I didn't. Well, it does. I don't know what you mean by a graph structure, but if you remember the picture I had, you remember I had a bunch of points. This is the embedding. Suppose those are the arcs with, for example, V1, V2, V3, V4, V5. Now, my network N consists of the union of all points that you see either at the vertex locations, the V1 up to V5, or along the black lines. Okay? So, because of the assumption I said I mentioned somewhere in one of the previous boards, I said that the embedding can be carried out in such a way that the arcs intersect at most one endpoint, okay? And because of the connectedness assumption, you will definitely end up with a connected structure here, which has the same topology as the initial network. Do you see why? Because, for example, T12 of 0 is V1, and also T14 of 0 is also V1. So they have to actually have this particular structure, okay? All right, so it does have a graph structure, if that's what you mean. Now, that definition is pretty important. Because the function d, which maps pairs of points to the reals, satisfies the following. There are three important properties it satisfies. For every pair of points x and y picked from the point set n, we have number one property, the value assigned to dxy is always non-negative. Why? Because it's a length function. The length of a path is either 0 or positive. Okay? It's always non-negative, and it will be 0 if and only if x is the same point as y. Otherwise, because we assumed positive lengths for the edges, of course it will be positive. Okay? That's called non-negativity. Number two, whatever value you assign to the pair xy, it will be the same as the value you assign to the pair yx. It's symmetric. This is true for every xy. Okay, I wrote the for every xy. In the exam, if you happen to give me these axioms or properties, if you forget this at the beginning, you have to write it here. Please don't forget these things. This cannot be true only for one pair or some pairs. It has to be true for every pair. These things are, even though they look kind of superfluous to you at the moment, when you start speaking about rigorous approaches to problems, these things become important, okay? So please be careful. It's a matter of disciplining your mind in these things. All right, number three. This is called symmetry. And number three, the triangle inequality, you know that. The distance or the value assigned to pair xy is never any larger than the value assigned to xu plus the value assigned to uy for every u in n. It's always less or equal. So, non-negativity, symmetry, what else? Triangle inequality. Now it turns out that if you have a set n together with a function d defined on pairs of points of the set n, then as long as d satisfies these axioms or properties, it's called a metric space. That's an important definition in mathematics, okay? So this is a well-defined metric space. Some people write it this way. Some people say n is a well-defined metric space with distance function d or distance d, whatever. These are different terminologies. They all mean the same thing. Okay. So this is sort of the background information. From this point on, we can actually start carrying this out for more down-to-earth problems, such as the minisum problem or the minimax problem I mentioned at the beginning. Okay? Whenever you talk about the distance function, if you fix one of the endpoints of the paths under consideration, in other words, suppose you fix y, then the function d as a function of x alone is continuous on n. Why? Anybody? Intuitively. Why do you think it's continuous on n? Just intuitively. I mean, we don't have to go into the delta epsilon definition of continuity. Yes?
This will go, we can actually define a path from any point to the point y, because if we can define a path, then at first it's the shortest path if there's only one path, and if there is no path, then they're not connected.
Well, there will be a path, because when the network is connected, regardless of which pair of points you pick, there will be a path. So the length will be finite. The network is connected by assumption. I said that from the very beginning. So in case that's not clear, the network n cap, it was assumed to be connected at the very beginning. I wrote it down, I believe. And so the embedding will also be connected because of the way we carry out the embedding. Okay? So everything under consideration from this point on in the rest of the semester is connected, all the transportation networks we have, unless otherwise mentioned. Okay? All right, now for this, of course, it's the same thing here. This is also continuous. This is pretty straightforward intuitively. I'm not going to go into rigorous definitions here, but let's just look at the second one. If x is here, then, of course, you've got the rest of the network here. Y is some point here. There's some kind of a path here. You may have all kinds of paths everywhere, okay? But nevertheless, you've got some kind of a path here, and one of those paths will be shortest. And I'm in this case. When you start varying y a little bit, a little bit delta deviation from your present position, what happens? The lengths are varying according to the relations I gave you at the beginning. The subarc information, the length information, etc. Those are continuous variations. So the sum of the lengths of sub-edges and edges will be continuous. That's quite intuitive. Of course, you can give a rather rigorous proof of that if you need to. I'm not going to ask you that in the exam. Don't worry about that. Okay. All right, so it's continuous. So this continuity, as well as the compactness of the set, well, also I should mention that. Let's just also mention one thing here, which I forgot to mention. N is a compact set, which means in this context, it's bounded. What else? And it's closed. It contains every limit point. Have you seen some of these things in your 500 course? 500, yes. So there are some uses for these theorems. Why do you need, for example, extreme value theorem or intermediate value theorem? Well, you talk about minimizing a function. If you have a compact set, and if you have a continuous function or a function of a continuous function of a continuous function, then the existence of minimum is guaranteed. Otherwise, without those theorems, you wouldn't have that. Okay? All right. These may look mathematical subtleties, but we're going to use them either intuitively or, if we need to, sometimes rigorously. Okay? The continuity of D and compactness of N. Now, some of you are from undergraduate here. I know they are interested in this course because they just take special interest. Now, you guys don't probably have much idea of what these theorems might be. Don't worry too much about it. Just take for faith that they are useful, okay? Are the other people all comfortable with these theorems? Okay, you will be, maybe, in time. So from this point on, all the networks I talk about are embedded networks. So it's meaningful to speak of points along arcs. So let's pick an arc VP VQ of some embedded network N. Again, I'm assuming N is always connected and undirected. Okay? Ataberk. It's always connected by assumption and undirected. And what I'm going to do is, we're going to investigate or study the function D as a function of x for fixed y as x varies in the edge VP VQ. That's what we're going to do. So we have a fixed point y, and we're looking at the how the function changes as a function of x as x moves from one endpoint of the arc towards the other endpoint. Can be. But initially, I'm going to take it to be a vertex. But it can also be another point in interior.
It's also another vertex, not necessarily VP or VQ, right?
It can be one of VP and VQ. No problem with that.
No, it can be, but it doesn't have to be.
It doesn't have to be, no. So let's just write y in N, okay? It's any point in N. Let's take a 10-minute break, and then we'll continue with that.